I'm going to jump straight into organic. So let's jump down here. Organic compounds are compounds that are primarily made of carbon and hydrogen atoms bonded together. Let me give you an example. CH4, which is methane, is an example of an organic compound. Sometimes they may have other types of atoms mixed in, like chlorine or fluorine as an example. Okay? Inorganic compounds would basically be everything else. So all of the compounds are inorganic, meaning they are not organic. An example of an inorganic compound would be something like potassium phosphide. Okay? Okay. Now, binary compounds are made of only two different types of elements. Okay, so that means a binary compound could be methane, right? Because that's made of two different elements. It could also be my potassium phosphide example, because that's made of two elements, okay? Now, hydrocarbons, which you guys talked about in biology, which are made of primarily carbon and hydrogen atoms, those would be binary compounds. An example of a hydrocarbon would be something like C2H2. Okay. And then I think that's all we need to discuss there. Let's go to the next page. Okay. The top of this page goes over the differences between ionic and molecular compounds. So ionic compounds are made of ions. Ions are charged atoms or groups of atoms. So let me give you an example. Na+1 and Cl-1 would be examples of ions. You could actually have the hydroxide ion, which is OH-1, or the phosphate ion, which is PO4-3. That would be a group of atoms with a charge. When you bring together ions, you make ionic compounds. So ionic compounds are made of positively and negatively charged ions, and they're held together because their opposite charges attract each other. And they arrange themselves in really unique crystal structures called ionic lattices. And these are really stable, strong structures. So here is an example of an ionic crystal lattice. Notice the ionic crystal lattice has alternating positive and negative charges throughout, and that's what makes the structure so strong. Okay? Now, the attractive forces between them would be ionic bonds. So the bonds that hold the oppositely charged ions together are ionic bonds. So here we have table salt. Table salt is sodium chloride, or NaCl. Sodium is a cation, chloride is an anion, and they're held together with ionic bonds. Now, if I'm talking about something called molecular compounds are a little bit different. The main difference is going to be this. Ionic compounds, these contain a metal or the ammonium ion, which is at the bottom left of your periodic table. Okay? So table salt is ionic because sodium is a metal. It's on the left-hand side of your periodic table. Now, molecular compounds, these are made of non-metals only, which are on the right-hand side of your periodic table. Okay? And non-metals tend to share valence electrons. That's how they form bonds and are held together. And so they form something called covalent bonds. And there are no charged particles in molecular compounds. And they call molecular compounds molecules. Okay, so these molecules are neutral, and they're just a bunch of nonmetals attached to each other. We good? So here, this is an example of water. Water would be a molecular compound because hydrogen and oxygen are considered to be nonmetals, here's oxygen, and then here are your hydrogens. Okay, so what we're going to do is take a look at the practice problems at the bottom of the page. We're going to classify things as either being ionic. Can I move the page down? Yeah. As either being ionic or molecular. So remember, ionic means it has to have a metal or the ammonium ion present. Molecular is all nonmetals. What would CO2 be? Yeah, this would be molecular because those are both nonmetals. How about calcium fluoride in B? Ionic. Yeah, ionic because calcium is a metal. And then C. Molecular. Yeah, molecular because they're both nonmetals. And then D. Yep, ionic because magnesium is a metal. And then E. Yep, ionic because lithium is a metal. And then the last one, ammonium chloride. Ionic. Yep, ionic because this is the ammonium ion. We good? Let's look at the next page. Let's talk about acids versus bases versus salts. Okay, acids have a hydrogen ion. They will typically start with a hydrogen. And then they're going to have an anion attached. And we'll figure out in the section 2.4 more, we'll talk more about anions at that time. But here you can see how I've got a hydrogen leading the formula in all three examples, okay? Acids are technically a special type of molecular compound. And when we dissolve these in water, they actually will disassociate or separate into the ions that they're made of, okay? In terms of bases contain a hydroxide. So remember, this is on the bottom left of your periodic table. It is OH -1. So when you see an OH typically on the end attached to a metal, that's when you know it's a base. So some examples would be NaOH, CaOH2, and AlOH3, okay? And I would make a note here, this is a metal. This is your hydroxide. I don't want you to confuse this with alcohols. Alcohols have an OH in them as well, but those are hydrocarbons or more organic molecules, okay? And then lastly, we have salts. Salts are also ionic compounds, but they cannot have a hydroxide in them, okay? Now, generally speaking, the chemical reaction that you will have for acids and bases, like I have here, I have an acid reacting with a base. So this acid begins with hydrogen, that's hydrochloric acid, combining with sodium hydroxide. It's a base because it has a hydroxide. This will produce a salt and water, okay? These types of chemical reactions are called neutralization reactions. We'll talk more about that in chapter 4. Okay, let's take a look at the quick check. It says circle the correct response. Number 1, salts are ionic or molecular? Ionic. Ionic, perfect. Number 2, magnesium hydroxide is an acid, base, or salt? Base. Base, good job. Number 3, silver bromide is an acid, base, or salt? Salt. Good job. Let's go on to classifying mixtures, and then this is the last part of this section, okay? Okay. Mixtures can be the same throughout, or they won't be. So that means they're either heterogeneous or homogeneous. So homogeneous will look the same throughout. Heterogeneous will not. Homogeneous mixtures could be one of two things. It could be a solution, like seawater, as an example, or it could be a colloid. Colloids are going to have larger particles dispersed throughout them, and these will reflect light. So fog would be an example of a colloid, okay? Now, homogeneous mixtures, which are also known as solutions, generally speaking, appear the same throughout, and the particles that are in it are really, really small. So like salt particles that are dissolved in seawater are really small, and I can't filter them out. I would have to distill salt water to get the water to leave and leave the salt behind, or evaporate the water, okay? Heterogeneous mixtures do not appear the same throughout, and they generally will have some particles that are pretty large that you can sort of visibly see with the naked eye, and you can often pick things out of it. Let's go to the next page. Okay. Solutions are primarily made of two different things, a solute and a solvent. The solute is the lesser component or the minor component. It is generally what is being dissolved. So if we're making salt water, the salt would be your solute. The solvent is the major component in the mixture, and it generally does the dissolving. So that means water would be your solvent. Okay, when something is dissolved in water, we say that it is an aqueous solution. So an aqueous solution will often have an AQ after it in parentheses, indicating that it is dissolved in water. Okay, most of the stuff that we deal with in nature is going to be dissolved in water. I think that's all I have to highlight on that. Let's go down here for examples of solutions. Okay. So down here, they give you some examples of solutions. Salt water, the most common one. Steel and bronze. These would be solid solution examples. You can have solid, liquid, and gaseous solutions. Okay. They will look the same throughout. Another example would be something like stainless steel. Okay. Gasoline is an example of a liquid solution. Technically, gasoline is a mixture of different hydrocarbons. And then air is the most common gaseous solution. Air looks the same. Okay. And then lastly, let's talk about colloids. And then remind me to look at your periodic table so that we can label the different columns with their particular names. I just want to make sure that you understand that before you leave, okay? Okay, colloids have larger particles dispersed throughout them. You may want to read through this later. If you've got a liquid that is cloudy, then it is either going to be a colloid or a heterogeneous mixture. How would I tell the difference? Shine a light through it. When you shine a light through a colloid, what happens is the light will be deflected by the really large particles that are in a colloid. So that's why when you guys drive through fog, shining light in fog doesn't help you see any better, right? It makes it worse. And that's because the particles in fog are so large that they will scatter the light. This concept is known as the Tyndall effect. Okay, let's take a look at the next page. I gotta stop this.